Thanks to the mass spectrometer, we have a way of comparing the mass of atoms. Their masses are directly related to the distance they travel through a magnetic field. The mass spectrometer has given us relative masses for nearly every known isotope of every kind of atom. What we need now is an effective way of using this information in the laboratory. Ideally, we'd like to use a balance scale to compare masses. Though it can't measure the mass of an individual atom, it is a practical working tool. We've developed one method for using a balance scale to mass atoms. Two equal volumes of a gas, which contain the same number of molecules, can be compared on a balance. We are also comparing the mass of individual molecules. And if we know the number of atoms per molecule, we have a practical tool for comparing the mass of atoms. Gas volumes give us a way of working with atoms, using a standard laboratory scale. But this method can't help us with substances that are not normally gases, like lead or iron. We need a more general container that always holds the same number of atoms, no matter whether the substance is solid, liquid, or gas. Well, one useful container might be a number. Think about it. If we always pick the same number of atoms, we always have the same number of atoms. Oh, that's so simple it hurts the head. But what number? Try anyone. Oh, a nice round number out of thin air, like 1,000,000. Call this number an aardvark, after Henry Aardvark, the first man to count to 1,000,000. Place an aardvark of two different atoms on a balance. Now we can directly compare the mass of individual atoms. But there's a catch, isn't there? We can't count the atoms, so how do we know we've got an aardvark? We don't. It's a nice number, the aardvark, but not terribly useful. What we need is a more useful number. Scientists decided that 12 grams of the isotope carbon-12 contained a useful number of atoms. They didn't even care what the number was. It seemed so useful that they gave the number a name. They called it Avogadro's number. Now, what could possibly be so useful about the number of atoms in 12 grams of carbon-12? It's all fiendishly clever. The relative atomic mass of carbon-12 is 12. And the relative atomic mass of hydrogen is 1. This mass ratio is the same whether we compare single atoms or groups of 4 or even 1,000,000. The ratio is the same if we compare any equal number of atoms, including Avogadro's number of atoms. So, Avogadro's number of carbon atoms has 12 times the mass of Avogadro's number of hydrogen atoms. And we ourselves decided that Avogadro's number of carbon atoms has a mass of 12 grams. It follows that Avogadro's number of hydrogen atoms has a mass of 1 gram. In the same way, even though we don't know what the actual number is, we know the mass of Avogadro's number of sulfur is 32 grams, and so on. Because of how this number was chosen, it's a practical tool in the laboratory. It's only necessary to look up the relative atomic mass of any element. Then mass that amount out in grams. This amount of a substance always contains the same number of atoms. At last, we've found our universal standard container. It's an amount of substance, the atomic mass of any element measured in grams. This universal container is called a mole. In chemical reactions, the mole can be used to measure not only atoms, but also molecules. The mass of a mole of iron atoms is 55.8 grams. The mass of a mole of sulfur atoms is 32.1 grams. So the mass of a mole of iron 2 sulfide is simply 87.9 grams. The mole can also be used as a standard gas container. A fixed number of molecules at a fixed pressure and temperature fits in its fixed volume. Let's choose a standard pressure. Atmospheric pressure at sea level, or 101.3 kilopascals. And a standard temperature, the freezing point of water, 273 Kelvin. Now for a fixed number. Why not Avogadro's number? What volume would it fill? The answer? 22.4 liters at standard temperature and pressure. 22.4 liters of any gas at standard temperature and pressure always contains a mole of molecules. Are you curious about Avogadro's number? Although you don't need to know the number to work with the mole, Avogadro's number has been estimated. Not very neat, is it? So, 1 mole of atoms contains 6.023 times 10 to the 23rd atoms. And 1 mole of molecules contains 6.023 times 10 to the 23rd molecules. This amount of substance, the mole, is a useful working tool for exploring chemical reactions. A practical universal container for either atoms or molecules. A container that always holds the same number. A container we can mass in a laboratory. A container to compare the mass of individual atoms and molecules as they combine and recombine in chemical reactions.